So anyway, thanks for coming, everybody. We'll just go ahead and get started. We do have pizza on the way, so that's coming in. There's drinks back there. Welcome to Data Masters. Thank you very much for coming. We generally try to keep it relatively loose and you know, kind of casual, so feel free to get up, grab drinks throughout the evening, ask questions. That's pretty much, you know, it really is an open forum. So anybody in here really warm besides me? Okay. All right, so I'll talk to Charles about that when he comes back in, because I'm like sweating. But anyway, so I guess we're going to go ahead and kick it off. What we've been doing here at Data Masters is we've had a couple now. We're doing sort of a series of presentations on case studies. If we have guest speakers come out and give a case study on something that they're working on or a particular technology challenge related to data. And then we open up a forum where people can just discuss those problems, those challenges, what they've been facing, and how they work around it, things like that. We found it very useful for people who are facing those same challenges or just want to learn more. So this particular event today, awesome. So today we're talking about data graphing. So it's going to be really good. Data graphing, and if you're not aware what data graphing is, think about it as taking your data, like data about people, and you can build a network about people, so you can see who's related to who. And then you can do an analysis on that network of people. You can say, well, this person's related to this person, this one's related to 5 more. And it doesn't have to be about people. It can be about anything. It can be about, you know, in this case, we're going to be talking about music and movies, but you can do data graphing on, you know, books, about storylines. You can do all sorts of graphing with it. It comes in very handy. So, very first, before we do anything, special thanks to Rocker Labs. Charles Walker, sticking it up in the back.
Yes.
Yeah, so do you understand what I'm talking about Rocker Labs?
Sure. So Rocker Labs, we partner with entrepreneurs and we provide them a core team to help them get their companies co-built. So we partner with them, we provide them a chief product architect and an engineer, and we get them to an MVP stage and then hopefully get them additional funding so they can then move on and really launch their companies. And a whole suite of digital products are coming out. There's really 20 companies in the portfolio, and many more to come.
Awesome. So yeah, so Rocker Labs has been sponsoring Data Masters for several months now, so we generally hold meetups here in the spirit of the community there. They bring in various groups and let us use the space and whatnot, so special thanks to them for that. And also special thanks to Ranger Technical Resources. They are a staffing and consulting agency. They're actually based out of Fort Lauderdale. Brian Nunez, currently not here. I don't know if, you know, maybe guess I can travel or something. He's usually here. But they provide the sponsorship, so they pay for the food, the pizza, the drinks, and all that stuff. So special thanks to them. I give a quick bio about myself. I've been working about 15 years with database technologies. Started off in the Oracle world, and that quickly spread to other areas with open source stuff, MySQL, SQL Server. Well, SQL Server is not open source, but it's not a database. Postgres, worked a lot with NoSQL stuff now, so Redis, Mongo, Couchbase, Cassandra, Neo4j, and a few others. I've had the good opportunities to work across many industries. I had a lot of opportunities to work in different fields: retail, consulting, energy, marketing, gaming companies. And that has really given me an interesting advantage to see how different industries use data. And that's been you know, useful for me to get that kind of insight. So when I work, you know, start looking at a project, you know, I can look at it from different angles. Every company pretty much has data, but every company does it slightly different. And it's really interesting to see how they do it, how they handle scaling, how they handle data integrity. Really fascinating stuff. So this is my website here. This is my blog. So after the meetup event, I'll be, you know, probably this weekend, I'll be posting the video, the slides, and any other materials that we have, and pictures. I'll be posting them on my blog. So there's also my email there. So if you have any questions, you can feel free to shoot me an email. And that's also my Twitter. If you care to look at my random tweets, then by all means, go right ahead. And we also have Fausto, who is from Senzari. Senzari is going to be giving us our case study on data graphing. Senzari is a company where they do data graphing for music and music industries. Music and movie industries. And they have built a highly targeted recommendation engine based on this data. And I just just think about this for a second, just how much music is out there in the world, how many artists, how many songs, and they craft this data to find interesting relationships between data, between fans, between artists, between songs, and they can generate a recommendation engine as a service that other companies can consume or other products can consume, and they can build applications around that. Very context-aware, very personalized data intelligence for entertainment choices. And our speaker tonight is Fausto Fleites. Okay, I said it right. So he's the VP of Data Science at Senzari, so he runs the data show over there. PhD in computer science from FIU, expert in distributed data analysis, machine learning, and OLTP graph queries. Suffice it to say, he knows what he's talking about. Basically with that, we'll go ahead and get started. Was the pizza here? Not quite yet?
Not quite yet.
All right. So we had another guest in there, right? Awesome. All right, welcome. Welcome, everybody. So we're going to go ahead and get started. Let me just hand it over to Fausto. Thank you all for coming. Enjoy yourselves. And like I said, it's fairly open, very casual, so feel free to get drinks, go to the bathroom, ask questions. So we're really here for you guys. So welcome. Thank you. Thanks. No, it should be the other entry on this one. No, there's just for. I'm just trying to find out.
I could restart the, yeah.
Sure.
I was going to restart the app.
I don't think we can use it. I think they found it. Maybe. No, it's the Wi-Fi still standing. There we go. Awesome. Slide type forward.
Well, thank you for the introduction. Welcome everyone. It's great to be here. So, as you said, I'm going to be talking about graph databases, high-level overview of how do you compartment between graph with the traditional model, and how do you showcase a specific case study of how you use a music branch dataset. I don't know if some of you know it. Music branch dataset is an open source database and server for music information around the world. It contains about 29 million tracks, 2 million artists, the releases across various countries, languages, pretty much all the information you can get online for free for music therapy. Before I start traversing nodes and edges in the graph, I'll first describe the relational model, high-level overview, how we use different relationships versus nodes, and how the graph model takes a different approach towards relationships in the following domain. Then we talk about graph databases, three of the most common ones, and specifically I want to go over the details of typing, which is one of the kind of the new graph databases distributed, and how we leverage the Senzari to achieve a fully elastic distributed architecture. And then discuss the basics of kernel, which is a query language. It sounds like Java plus Ruby. That's what all the features of full language for querying graph. And once we know all the basic details about querying graphs and storage features, so we can go over the overall ETL process for putting music brands in a type database, and then how do we do queries in the graph and derive some insight using simple ETL graph traversal. Well, as we all know, the relational databases have been still the backbone of software applications, and the most most commonly used model for data storage. They structure data into tables that have a specified set of columns, specified set of data types, and basically, usually a table corresponds to an entity in the following domain, and a row in that table is kind of a specific object, a person, for example, in your following domain. Relationships, on the other hand, they're kind of different. They are treated as second-class citizens, if you call it that way. For example, if you want to reference a relationship into two tables, the most simplest one is a many-to-one relationship, and then you have a column in your one table designated as a foreign key, and then that values in that column reference in the primary key or primary key in another table, and that's then you need to in runtime compute. You have to join those two tables to obtain your relationship. So it has a you need to compute the relationship. You cannot just retrieve from the database. That's why they're called second-class citizens. And this join operation is complex. You need to find values in your foreign key column, searches in the other one, do complicated operations to split it up. And you have another type of relationship, which is many-to-many, in which you cannot just do, you need a third table besides your two tables. You need a joint table, and this complicates the joint process a little bit more. We can look at very simple example here. You have objects that have users, and then you have a many relationship of users that like artists. So you need a third table to represent this many relationship, and then to actually obtain the list of users, the list of items that a user likes, you need to actually compute the joint contract and to obtain that relationship. Graph modeling takes a completely different approach. It makes relationships first-class citizens in your foreign domain. They don't have to be computed in runtime. And it allows you to model your foreign domain more intuitively. Basically, if you think of a database structure, it kind of resembles your foreign domain. And you don't have to think about rows and joint tables. It models data, basically each record, the record that you have in your tables, in your SQL database will be stored in vertices or nodes in this graph. And the properties of this, the values of the columns of that record will be properties of this node. And relationships between nodes are stored as edges. So edges is considered of pre-compute joins. So each node has a set of edges or spatial type nodes that already tell you what are the other nodes in the graph with whom that vertex has a relationship. So you skip that process of searching the value and searching another table. That process completely skips. So you can go directly to that ID and pick your relationship. And the way you interface with the graph database is very simple. Say, okay, this node you need to compute. It's sort of almost all one operation. You need to actually compute that going on the fly. As I said, vertices usually store the edges, so you skip that part of the join operation, and it makes it very fast. Also, usually most of, if not all, the graph databases they don't allow you to define schema. You can kind of schema it, so they follow this paradigm of NoSQL databases, and you achieve more scalability by using constraints and denormalizing the data. We can look at some very simple example with the entity domain. You have artists, you have tracks, and users can like analyze this into a track box. So you have an actual. So you have an actual vertex, for example, for Adele. You have properties there. You have the name. You can generate library properties in one. Usually you designate a spatial property as a type, so you can search for all the vertices at the same time. That's like searching for having a column of how many tables of the artists in the SQL database. You have vertices for tracks. You're the same property duration of every one. And then you have an edge from Adele to all, and for each track that belongs to Adele. You can actually very quickly either cross the rest and go from here to here and process this track. And you have a user that has edges to the artist they like and the track they listen to, and you can actually assign properties, any kind of property, to the edges that they have. And this kind of graph is not the textbook graph. In the textbook graph, you don't have properties assigned to anything. It's called property graphs, which is what the most databases, graph databases model. They allow you to assign properties and make it more powerful. So, as I said, one of the things for graph is that it allows you to do more intuitive model of your foreign domain. In addition, with the type of queries they have, it's called graph traversal. Basically, you go to a set of nodes and then you traverse edges and then you transform and then you keep on traversing the graph as many features as you want. It allows for a very powerful query language. And then you can do with this, once you have your data stored in the graph, you can do some sort of new analysis. You can do page rank. to identify kind of importance of the nodes in this network. You can do centrality, where the nodes are most essential to make more important. You can do path separation, you can find between these two nodes, give you all the paths that link them, and you can derive inside. For example, in the space of give recommendation, I give you a recommendation of two I's and say, okay, yeah, these two are similar, but why? If I give you all the paths between them, you say, okay, they have the same producing in some, they're from the same team, they collaborate together in this reporting. And then you can say, yeah, there's some I's, and you can give some explanation by describing all the paths of two nodes in the background. Graph database, this is the most popular one, Neo4j, which Andrew mentioned, OMDB and Time, which is the one I want to subsequently describe. Neo4j is the most widely used. It's been online the longest, and it has very nice features, a lot more things than the other ones, but they make actually dealing with the graph already easier. However, one problem with Neo4j is that each node in the cluster has a copy of the data. It follows a master-slave replication. So the size of your graph is constrained by the capacity of the disk in each node or memory in the node. So they have a limitation, which for most companies doesn't matter. If you want to do really bad, a large graph, that will be a constraint for you. ORMDB started that way. However, back in 2012, they changed to a new backend storage called Pesocast, which is a distributed in-memory database. We call it a distributed version, in-memory version of Cassandra. And then the database I'm going to talk about is very recent, started around 2012 as well. And they actually leverage Cassandra Firebase as a fundamental storage. And by that, they allow, they guarantee you elastic scalability, no single point of failure, and they provide a very good feature for traversing the graph to a very language programming that I'm going to describe. And in the Titan case, probably now in the RNDB case, the size of your graph scales with the number of nodes you have in your cluster. It's not limited, since the graph is split between all the nodes. You can have more larger graph than you have with Neo4j. Titan, as I said, the graph that you can put there actually depends on how big your cluster. And it allows both OLAP and OLTP transaction processing. OLTP means like, you could build your e-commerce site with a backend database using Titan, and you have online transactions and transaction making. You can have ASIC consistency on your site. And OLAP is basically you can batch process your graph using Hadoop or Hadoop to derive insights of your data using a tool called funnels that allows you to connect Hadoop very easily with your graph in Cassandra.
Quick question.
Right.
Could you explain the part about the ACID transaction?
Right. They store the data in Cassandra, and using some mechanism with blocks and doing Cassandra, you can query your data using transaction. You can open a transaction and do one modification in the data, close the transaction, or it will guarantee you the ACID constraints. You could have also, you can lose them out and do eventual consistency, and then you can have better performance, you would say, but you have eventual consistency, meaning that at some point everyone's going to see the data in the same form, but at some point after a while they will actually see the same value of the data. With Cassandra, the Titan analysis do that or not depends on the actual data storage they use. With Cassandra, you can have eventual consistency if you use it the way you query Cassandra, or you can have, I don't know how many of you know, you can query using a form of the replication in your node, and then you can assure that you always use the same value of the data. If you have, for example, Netflix, which is one of the people that is Cassandra Darkstore. The thing, that feature that you're watching the show, and then you go to another room and you switch channels and you choose the device and you still choose the same version of the show, you need a very strong consistency in being able to determine where part of the show you go watching. And they do that by a kind of query to Cassandra that's called the quorum query. A quorum means that you have, basically in this distributed data source, what you do is that you have beside having multiple servers that allows you to withstand nodes in your cluster. Basically, usually you have at least 3 copies of each data element. So if I query a form, it means that I'm going to at least check the value is 2 out of 3. So make sure that I get the right value. If I lose my consistency, for example, I want to read a track from an artist. I really don't, maybe the track's another day, I really don't care if I don't read by now the track that I had a second ago. Usually, you know the tracks already in the database, so I can read with consistency one name. The first node that I hit in the cluster, I read that value, and that's it. I don't need to check the other node. So that this kind of mechanisms of eventual persisting. As I said, there is Cassandra.
So it actually has Cassandra as a backend for the storage engine?
Think of Titan as a library.
Okay.
And you have to manage Cassandra separately. So when the things are you connect to and ingest data into Cassandra, you have to use the library, and they have the way of storing data in Cassandra.
So the data is stored in Cassandra,
Right.
and then Titan is essentially a layer above that, like a translation layer.
Right.
You talk to Titan, Titan pulls the data out of Cassandra, graphs it, and then hands you back the results.
Yes.
Okay.
All right.
So if I use the Microsoft Azure Media Services,
Right.
we don't have that problem. It's because they use something like a something in the web phone, or because we are an alternative.
Well, actually, Microsoft Azure is sort of a cluster. It doesn't specify Cassandra itself.
There is geographical verification, so I just use my service and they take care of all that.
Yeah, but Azure is similar to MapReduce, right? It's to SDFS. Azure, Microsoft Azure is similar to SDFS. It's different from online transaction processing database. For example, in the Hadoop world, right? MapReduce, right? This is what's called a distributed file system. So you have replication, and you can store your extremely large data set, but you cannot put one record there in less than 10 milliseconds, right? You need to batch processing driver. So that's why Azure gives you a compute platform. It does not give you a database on which you can, like Cassandra, which you can do like SQL queries and retrieve data very quickly. You can install Cassandra in Azure.
Yeah, so consider Azure and others like it. So there's Amazon, like AWS, Microsoft has Azure. Those are basically the equivalent of cloud-based data centers. So think about a data center where you just have rows of servers. They're just blank servers. Well, Azure is the same way. It's cloud servers. So you can sign up and you can use their servers and you can put whatever you want on it. It's just a bunch of computers.
Actually, media services are
Yes.
football, API,
Yes.
pass.
So in addition to so that's the first layer, which is basically the infrastructure as a service, and then the next layer above that is the platform as a service, where they have those types of capabilities, media services. They do have some database as a service. They have like relational databases. I don't really know of any provider right now that is either giving Cassandra as a service or graphing as a service. I don't know of any providers that are currently doing
Graph, no. DataStax is working on a graph version of Cassandra. Now, for example, if you go to Google Cloud, right now you can say you can create a cluster in the computer platform and say I want 10 machines and install Cassandra development. So you would have a micro cluster for yourself with 10 virtual machines in Google Cloud and install Cassandra based on the cluster. You can do the same thing in-house. DataStax, which is one of the companies that provide corporate services on top of Cassandra, they give you what's called an AMI, which is a virtual machine that you run on AWS, so you can create a cluster very simple with a few clicks and have your Cassandra running. So as Sanjay said, this is a platform as a service. You can rent machines. Now, Amazon, besides that, same as Windows, I'm not sure, they provide already software as a service. For example, you're gonna have Amazon has something called Amazon DynamoDB, right? It's the same thing. You say, okay, create a DynamoDB, assign 3 nodes, and I want to store data on it. You don't need to install anything like that. So you trust Amazon to manage your data.
Right.
Right.
So it's an alternative.
But you don't have any graph technology or library to put your data as a graph in Amazon DynamoDB. Right now, the graph
I am
technology.
familiar with Microsoft, and I have a way in which I can even define this is in Singapore and London.
Right, your traditional data. Now, the thing about graphs, it's a specific type of database. Right? All these services allow you to have SQL databases already as a service and no SQL database as a service. Each one has their own version. But graph databases, I don't know any one of those yet. It's a very nascent technology. If you want to have your graph database, you're going to have to install the software, put everything in Amazon or wherever you want, and handle it yourself.
So graph is an alternative to Hadoop, SQL, and no SQL.
No SQL, okay, you have SQL for modern data, you have no SQL, and then you have graph, which is
A third kind.
you could think about an advanced version of NoSQL. Graphs usually have NoSQL stores.
Okay, let's go to that.
That was my question, was that, was graph different, or was it like inside of NoSQL?
For example, let's do this way. So Cassandra gives you NoSQL database, right?
Right.
So what understand you get your data and they actually structure it in a way
Okay.
so that you can actually grab data and pre-compute these edges and everything. I could do what I don't know. I could store data, but basically I would have to be writing the code to manipulate my edges, about to pre-compute the ones to happen there, or about to write a query language to traverse it. So all that is already provided about the I could get the secret, it's just that I have to spend my life doing joins.
Okay, we're coming to the data. I'm very sorry for missing the call.
Right? If I put in one of the NoSQL, I have to do the same thing, even though it's NoSQL database, because they don't have the already built in the concept of edges. You have to do it yourself. Let's say you will retrieve, let's say you put in an MSQL database one. You store one document with artists, one document with tracks. And somehow you need to encode the edges, right? How the tracks belongs to the artist. Either you put another document that represents edges, or you encode these artists with the name of the track they have. And then once you want to retrieve the tracks that belong to an artist, you have to get this artist, get the track, do a search, get the document. So all that is handled more efficiently for you by this graph database. It's just a model. It's just a model to do the data. At the end, it's just rows.
Is this a formal or informal?
Hadoop is not for Hadoop is for batch processing. You take your entire data set, and let's say that I want to have a graph, and I will use Hadoop to have a distributed computing platform to batch process the entire thing and compute centrally. For example, Facebook. They would actually know who in Facebook has more friends and they have more connections. So if I influence that people, maybe I influence the other one. So they do batch analysis using Hadoop or Spark, which is another version of Hadoop. They batch analyze the entire Facebook and they find the people that are more important in the community. Now, if you want to query right now what was in my data post, that's called online transaction. You need to sort of have the same, you need to have a database. Let's query that very quickly. Hadoop is not for querying, it's for batch processing. You cannot go and query one record in Hadoop. Take more than 5 seconds to this. You have to initialize it with some streams and where you find it and immediately use it. Okay, so with Cassandra, which is the actual storage.
I had a question about the edges. Can you have constraints on, say, types of nodes and have edges between them?
The edges, you get them yourself. When you ingest the data in your back, you actually say, okay, for example, let's say that you have already your music data set, right? And then you have music, and you start liking artists, right? Once they do the like, let's say, I like this artist, you actually find the artist, find the user, and say, add this edge.
Yeah, so you like said, there's a user and an artist, and likes go from users to artists.
Right, yes.
So these are types of nodes, right?
Right, but the types and constraints and data integrity in this NoSQL, which graphs are, and most of them are handled in the application side. You don't have, like in SQL databases that you say constraint and you actually blow up your transaction because you didn't do the right type. And that happens not with graph and all NoSQL. You have to take the responsibility in your application to maintain data integrity. And that's sort of the trade-off between having more scalability and performance versus speed. So you have to do some more.
It's not even an option.
For example, yeah, right. For example, in China, for example, you can say an edge has these properties with these types. So if you mess up with the types, you will not even do that. But you can basically create an edge between anything you want. So if your application creates an edge instead of between the artist and the user instead of a user and a track, then you have a problem with the that's how that in the application side. So Cassandra, which is basically the continuous availability with no single point of failure. For example, all nodes in a Cassandra cluster are equal. There's no massive. So all of them can communicate with the protocol called classic. Basically, they essential like a classic protocol, what they have and which nodes are present in the cluster. So if one node goes down and you have to replicate, you have the data replicated, and on one node you don't lose your data, and your application doesn't even know that. The other one is that you don't have a wide bottleneck. For example, in a traditional replication of SQL is that you have one master several stages, so you read something very fast, then you have to, your writes have to go to a master. If that master dies, then you have a problem. Right? In Cassandra, since all nodes are equal, you can write and read from anything. Beginning replication across data centers is actually very cool. You can define logically this cluster, this set of machines is in the US, this is my primary data center. I'm going to have a backup data center in Europe.
If you write to the data center in the US, Cassandra would automatically asynchronously and respond to you, replicate the data to the other one. You don't have to do anything, just define a different data center that will do it for you. This is so that the needs that actually use it to provide worldwide services, so streaming off, everything off, awesome. They have a caching layer to retrieve faster nodes in the database. And by elastic scalability means that you can add or remove nodes to the cluster by your application is running. They said they have a metric system. You have to measure the application. They start seeing that you have to train your queries start taking longer because they have a spike in usage. You can build a mechanism to add nodes to your cluster, and the machine will actually distribute the data automatically, and your load will then go down. Your performance will. So running into the program.
I'm sorry, I didn't mean to interrupt. I just wanted to let everybody know the pizza's here. So if you want to grab a slice of pizza while we're doing the presentation, then feel free to go ahead. But otherwise, continue.
So how do you query graphs, right? So one of the most commonly, pretty much all databases support this query-eligible programming. And it's a graph first elastic. It's a different way. Now you don't have tables and joins and constraint and word clouds, but you have to think about ways to do it. They have to get nodes, traverse from edges, and from there get a grammar place in the graph. That's how you query there. And so programming is JVM-based, basically Java-based, but they have, versions in JVM-based versions of Python and Ruby and stuff. There are two types of ways when you search a graph. Java graph, you haven't searched anything yet. The first thing you need to do is find a set of versions, right? So that's what like a global search. You need to find a way to, let's say I want to find all the vertices that have the property type of artists. So you need to find a way to quickly find all those vertices using an index, similar to what you do with the SQL database. And Titan allows you to define indexes on queries, so on types. So if you assign a property called type, you define a B+3 index on it, you can quickly search in the graph all the vertices that are of type artists. So this is kind of done here. So you say G is Y, B is the way you type the query. And probably the value find all the value. So that will give you a set of vertices. And then once you have this set of vertices, you can do traversal operations. You can use stuff to go beyond this one, to traverse all the regions in the graph. So think about the traversal as steps in a pipe or an iterator in Java. Basically, you get a set of vertices, this is a set of vertices, and then you do something, you get another set. You do something, you get another set, and that's how you traverse it. So let's say that I find all the artists in this one, the indices, I have many artists already in my current stack, right? Then I can do traversals, so I can do filters, for example. So let's say that I want to select artists that are only one in the US. So you can do a filter operation on a property called country. So every once you have a new set of vertices, basically a selection of where in the system. You can do transformation. Let's say, okay, I have this vertices, now I want to output just one property, or I want to find a function of some of the others, so you do a transform operation, and then there's a new set of vertices that are component. You can do side effect, you can do root count, for example. I have a ton of edges assigned to me, right? I can take the labels out of the name of the edge and do a root count to find what is the distribution of the edges that I have. I actually show examples of these tests. And I put here a slide that sort of draws some part of the SQL. I use search, for example, as I said, you do select from a table for Alice. This is like searching, like doing a global search on the graph based on a property that has an index. If you do select only the artist name from the table, well, this is doing a global search on artist and then just saying, this is transfer, just give me this artist name, the value of the artist name, and you solve them all. They said that the same thing, but now you want to know the length and the number of characters in the artist's name, right? This is you do a search, give me the artist name, do a transform, and then you pass the name like this is an email function, and say, okay, give me the length of whatever value came to the previous term. And if I want to select all the artists that, countries in the US, it's another property, same thing, so I search for artists, and then I ask, you do a filter, I said, well, countries in the US, and they say, you this set of artists you have, and so then you can traverse them.
The second example, is that returning the artist name for all of them?
For all of them.
Oh, so list of artists.
Each step before the dot is going to have a set of vertices. If you just want, just go to a field, you can select, give me the first one, the second one, and give me a range. Yeah, each step is a set of vertices at the current stage in the graph.
So when you're,
For the pipe.
when you're building recommendation engines, and it's not such an explicit query, such as an artist or a country, how are you sort of modeling that profile?
Rendering gives you the full power of Java and Groovy. So you can do really complicated stuff. Basically, think of any program that you want to write in Java, you can do there as a parameter. Now, usually you don't want to do complicated stuff in real time because then your recommendation will take 10 seconds. So what people do is that they do batch analysis, they pre-compute this stuff, and they represent it as vertices or new edges. Then your recommendation becomes very simple. And so what you transfer sort of that complication to batch processing, you put new information in the graph. Since it's an OC, you can create whatever edges you want. Put them there, you can have a very dynamic structure, and then your recommendation could be just select these edges, run them by sport.
So you create almost like profiles of similar like users, so that's already
Let's say
prepared.
you have a very complex machine learning mechanism to decide what is our secret. Right? So what do? You take the odds and you create any unit. So for each odd, you have an edge, each similar arc. If I want to give you a recommendation, I get the odds, get the edges, find the similarity score, get the top songs, and I give you a recommendation.
And then when people are playing similar music, you start.
So when people are saying, well, you record the stuff in the graph, and then they say every day, every 2 days, you take that, do collaborative filtering, and then you can rearrange the scores in the edges or create new edges if you have more dynamic structure for your recommendation.
I have a question. You were talking about like everything, so I wonder how you make sure that the data, when you're doing the query, is the latest information, because you said that you batch process and you have a set of results.
Right, that one is how you want to query the database. For example, in Cassandra, which I told you to eventual consistency. If you want the real data, for example, what is the last song played by a user, you really want accurate data, right?
Yeah.
You have to write a form. So a form query in Cassandra. Form means that of the 3 values that Cassandra has a copy of, it will query 2 and decide whether it's the right value or not. So you can have that strong
But
consistency.
you can match just to make sure that
It will do, Cassandra will do for you. You need to say, I want to query this, and by the way, use form.
and that can be adjusted depending on the
Right, on the
application
query
environment.
type, on the query type.
Yeah, so the Cassandra itself has it built into its own query parser. That, like you said, when you pass it a special type of query and say, I want the quorum to decide the best data for my query. So you're telling it, make sure you know whatever the quorum is, and it's usually a majority of the servers. Because the data is that it's changing all the time. There's transactions coming in, and that transaction can land. You may have, let's say you had 10 nodes. A change to the data can initiate on any one of those nodes, wherever it happens to land. Maybe it lands on node 3. So it's going to change it there. Cassandra will make sure that change gets replicated out to the other nodes, so that way it's durable. So if a node ever goes down, it's at least 3 copies of it somewhere. When you go to query back, you can say, I want a quorum query, and Cassandra will make sure that whatever data it's giving you, that's the latest data, at least on at least two of the nodes, or whatever the quorum is, whatever the quorum number is, to make sure that multiple nodes agree that's the latest piece of data.
So that part of maintaining the data will be on Cassandra's side.
That's all you know about the field. There's quorum, there's all. You can tell Cassandra, just check everything, all the nodes they have. It just doesn't lower them. Okay, Brandon, so now that we know more or less where the graph, what are the characteristics of the graph modeling, how do you put data in the graph? So what's the overall ETL process you need to follow to put the data set in a graph, right? First, let's go over some of the basic elements of music brains. So I'll show the schema of music brains kind of how we go through that. They have artists, any kind of musician, they have artist brains, for example, we have radio switch fish brains. That's how artist brains, that's how we have video recordings. So I have many artist brains. We used to more like an after album from the later album in 1999. I've been released in many countries, so I released a real world movie that you can buy in stores in the country. A medium, like CD, release recording, for example, that when they actually do the sound recording in the studio. That was when I really wanted to arm. So they have tracks, the actual song that I'm using is CD. They have words which are the composition and actually maybe something that being audio recording. Labels that record artists, you have countries, people were born where they're released. You have faces which are many of the studio, but murals, analysis have many URLs was associated with the URL free group and this was the music from music. So that public scheme is just part of the entire scheme. They know what they need to go on the website or they work on any way and figure it out.
Can you use semantics, like meaning that trying to have different words to the or I mean, like, technically, any song, right? So just like find keywords in the song and then you can semantics.
So let's say that Thailand has a component to Elasticsearch. You want to see, so you can do full text search on cloud search and you can Elasticsearch or Apache Store, right? So if you say, in Thailand you can say this property, by the way, put it in this Elasticsearch cluster, and you can put the lyrics to the song. And then you can find, in grammar, you can find queries that will actually find pieces of words or phrases of the song and retrieve the vertices that have that property. So back to the schema is already normalized. You have types here, you have to know the time to know the type of URLs. This is the most normalized type of everything. So when you want to do queries on user brains, you have to do over joins. And it's fast. And so how do we put this in a so the overall ETL process is the tables, which are kind of entities in your model, right? The records of the tables become vertices. And to separate types, you put a special property called type, and you say this is analysis, this is chart. So the columns are the property, the set of properties assigned to the vertices. And then for the most query properties, you have to define indexes to do a fast search. But at the end, it's just another version of data. So you need to define indexes to find data quickly. But not type. You usually search for a name or an artist, you define an index on an artist name, find an index on the artist type. If you search for a title of the song, you define for the property title of the song, you define an index for it. So you can find all these vertices, but it's probably very quickly. And the foreign keys, the relationships, then you make an edge. So what do you say? You say, graph, add an edge between these two nodes. This is the name of the edge, and this is the property. So you have to do that, so you have the edge there. And join tables are edges as well, but if you have extra columns there, you specify time for example, anything, you can make them properties of the edge in the graph. But I put at the beginning, you have artists and users, and you have, when you have, and if you don't table of the middle, you can have another column say at the time they did that, right? So in the edge between the user and the artist, you say, oh, this is the edge, he liked it, and this time, this is the date when he did that. So let's move on, this is the date. And in NoSQL and in Graph, you want to consider denormalizing the data to speed up search queries, and otherwise you go back to running what you're doing many searches on finding the type of amount. Let's say that I have 29 million songs in music brains and 2 million artists, and then I define a property called type, a vertex called type, and it has one edge to each track and one edge to each artist. It doesn't make sense to me to do that because if I want to analyze all the tracks attached to a type, vertex is 29 million vertices. There's no way you're going to compute that in less than half a second. Right? So that way doesn't make any sense. So you want to normalize that type as just a public value and just have your application ensure that you put the right value. And this is not only graph, this is usually good for NoSQL model. For example, how does the graph look? So you have an artist with some properties, type, name, gender. You have the alias of variations with the name of the artist in different countries. You have edges. You can call the artist as alias to point to here. On an area, you have artists that were born in an area or that currently live in one area. So you have another type of vertex called area with edges there. You can have artist credits that point to the artist. An artist can have many credits. I'll show some examples later. A recording, have a length and a name, it belongs to an artist credit. And a release group, which is an album, also belongs to an artist credit. Then you have tracks that appear that belong to an artist credit. Releases. So an album may appear in multiple releases across countries, right? So you have many to one here. Many releases to the same one. You have an edge to each one. A release as an artist credit, and the release was in a different country. For example, let's say that because of the application you're building, you usually look for an artist, you need to retrieve quickly the tracks. So there's no point for me of going to the artist credit, and then from here designing my tracks. You have to do too many traverses. So if for your application it makes sense, that course is important for you, you would then analyze this path and batch create edges from the tracks to edge directly. So when you get the edge, you get the tracks. Otherwise, you have to do two loops. And just an example, well, you have your rows, links to artists and these groups, and labels that report releases in a specific area. So this is one of the normalization. I don't want to put a type, a vertex called type, because otherwise I'll be pointing to many objects. Doesn't make sense for me to do it. So I put type as a property here in the artist. And there's more normalization that you can do on the music grade side. So let's go over some queries, actual results. I put this most of the music grades that I said in the past days. I put them into a talent database, and I found some queries on it. These are actual results from music grades. So I want to find Taylor Swift. So I'm looking at the graph. I haven't found any vertex here. I can't do any vertex. So I define an index on the property. I put a prefix MB. So music grades artist name. So I want to say in this graph, do a search on an index on this property by Taylor Swift. Give me the first vertex you retrieve. I know there's only one. I get Taylor Swift and I assign it to a variable, to a vertex called Taylor. I have a reference to a vertex. It outputs by default this stuff, is the internal vertex ID. And then, okay, this is a transform. These all the properties that that vertex have. Okay, Taylor, the map, all of them. Beginning year in music grades, 1989, date, December 15th, type person that comes from music grades, the artist name, the gender, the song name. Now, I have the vertex and I just want the artist name. I don't want to see the whole thing. So you say, okay, Taylor dot, just a transform, just give me that property and I give you the feed. It's a very basic search. So I have my first vertex, only one. So my set is with one vertex. Now, let's find all the credits that Taylor Swift has, or the first 11. So I still have my vertex Taylor, and I say, let's do a transform. So in is the operator that means into this, traverse to all the edges that have this name, and get the vertex. Get the first 11, so I'm going to range operation here, and then I say, give me just the artist credit's name. So it took Taylor Swift to all the edges that say that have this name, artist credit has artist, that's the name that I defined. It went to them, and then I just took the first 11 and up with the credit name. You can see that all the credits, the first 11 credit name that Taylor Swift has in the music name.
How did you get the Japanese to come back?
Right, that's the first thing that came up. So music grades maintains all these artist grades across many countries. So that's an awesome data they have.
But you put in English, and you got back to Japanese, right? So you
Taylor Swift.
Right.
You put in English to find Taylor.
right.
And then Taylor has edges to other vertices that are credits. Those the credit names could be in any language.
Right. Okay. So you passed in the search criteria, and it found the node, and you're telling it to return back the name, and whatever's stored there, it just comes back.
Right. I found Taylor, and then I said traverse to your adjacent artist credit vertices. Just give me whatever name you have there. You should this property. Artist credit's name. And those other vertices have these names.
Gotcha.
You have Taylor Swift featuring that Ed Sheeran. Weird character. I don't know if he's Japanese.
It's Japanese.
Yeah. Taylor Swift by herself, but she has songs by herself, and all these facts are. So let's do, for example, how many artist credits does Taylor Swift? No. Let's find all the edges that Taylor Swift's credits have. So you say Taylor Swift, go to all the edges, all the vertices that are attached to you by these vertices, by these edges. Give me your edges, incoming or outgoing, because edges have directionality. I forgot to mention that. So you can say this vertex goes from here to there, so I have the direction. You're gonna go the opposite way. But you can, but it means the direction of the meaning of the edge. And then you count all of them. So if you take all the artist credits that Taylor Swift has, and you count all the edges that they have, that this artist credit have, I don't know, any kind of edge, yes, 720. Instead of finding all the edges, I want to find all the outgoing edges, 47 only. And all the incoming, I have 60, 54. The outgoing are probably these same ones. If you look at the schema, Analysis query has one outgoing, only outgoing edge is what is, all the rest are incoming. So the 47 one are the same ones that I traversed too. You just count them as a one. So these 47 are the same count of these ones that I already traversed. These are outgoing from the credits themselves, incoming to table, to the direction.
So the music brains artist credit has artist, that's an edge property? That's an edge?
You mean this one?
Yeah.
That's it, that the label, the name of the edge.
Name the
The special property name.
Okay.
They put the
Okay.
And then of all the URLs and all the tracks, you have 1,600 edges coming into the set of 47 credits associated with those.
How much work does the system have to do to search for the incoming versus the outgoing?
The edges in Titan, they store every vertex stores all the edges. So counting the edges is an O1 or on a very fast operation.
So an incoming and an
And they
outgoing.
are stored there.
And in the other.
And in the others, yeah.
So it's duplicate
Right.
index
Yeah,
data.
they do that triple very fast.
Yeah, it's done it for speed.
And they done for speed and they do some sort of compression. Actually, you can do online, they do some sort of compression. Also, they say they have too many vertices. They have a concept called vertex-centric index. If you say, for this vertex only, they say they have time. A user likes artists, and that user has like 100,000 artists. You want to search for the one that he did a month ago, right? Usually what you do, put a property in the edges. But then searching for that particular time requires scanning all the edges, usually, right? It's an open operation. Titan allows you to define on that edge, say, I want an index for you only on the property time. So it will build a B plus tree on the edge to store to quickly find all the edges at that particular time.
So consider the index kind of like a lookup structure, kind of like a dictionary, or like an index on a book. You can say, tell me what page are, picture frames on, and you can go to the index, it'll tell you on a list of pages that it's going to be in the book, and then you can jump to those pages. So when you build an index, you're actually taking all the values, searchable values. Let's say in this case, you're talking about the edges, so it grabs the information about the edges, it stores it in the structure with the actual disk address, the address on disk, where it will find all the related values. So it really is you're telling the computer, or you're telling Titan to say, go find these edges that I'm looking for with this label, and it comes back with all the disk addresses where it sits actually physically on disk, and goes straight to those locations. The alternative would be if you didn't have the index, that has no choice but to scan everything to go find it. So that's kind of like going page by page through a book trying to find a word, as opposed to hitting an index, looking it up and telling you what page it's on. So the index is really there just purely for speed.
So I mean, so our graph databases, do they tend to be like pretty storage intense? Really like, I mean, you get something back, obviously like you have this nice graph like database, but is
The trick is the duplicate more data, although they do something needs to do compression then to minimize that part and gain. But that's a trade-off usually in all computers, right? To gain speed, you usually have to store something.
Right. But if I want to play around with this, like, on a Postgres like database that's like 30 gigabytes, I might want to spin up something with like 90 gigabytes.
It's in all actuality, believe it or not, it's not that much more storage intensive than say another relational database. Like if you compare it to a MySQL or a Postgres, it's actually much more compute intensive. So a relational database is relatively simple. You've got this table relates to this table.
Right.
You can write a query to go hit those two tables together. It's got some caching mixed in.
Right.
But if you think about graphing, when you're walking a path, you start at one node, and that could branch out to 5 nodes. And each one of those nodes branches out to 5 nodes. And you're computing values along the way, and it starts to, it's like exponential. And then trying to store that information in memory as it continues to compute, it's very compute intensive. So, and that's one of the challenges with graph databases. Like think about walking through multiple nodes like Facebook. You have friends, your friends have friends, your friends' friends have friends. But like LinkedIn, you ever go to LinkedIn and you see your profile and then you click on somebody else's and it tells you that, oh, this person is in your 3rd level network. But it doesn't like that. How does it do that? Well, they have distributed graph databases where it's sharing that compute power across many computers, across many nodes, and it queries each one comes back with its own answer, and then there's a central coordinator that collates the results and sends it back. So it's that distribution across multiple nodes that makes it faster.
Okay, but you have more specific indexes too, as well. To help
Yes.
with that.
So yes, so those indexes are specifically there to first get the data out of the database,
Right.
and then there's the compute power to do something with it once you get that data back.
Right, and you also have, it's a sharded database too, so you have more, it's like a node
It can be sharded, so you have a piece here and a piece there. So
Right.
sharding is where you take your big data set and you break it down into chunks across multiple servers, and each one, like one would have, 1 through 5, the next one has 6 through 10, another one has 11 through 15, and you break it up by pieces, and each one has its share of it and does something with it and then returns the results back. So yes, you can shard it.
That's in addition to having like 3, nodes. You're saying sharding is different than just saying I have a 3-node Cassandra database.
Well, you can have a cluster, and then how you store that data is up to you. You can shard it, or you can replicate it. So you can say, I have 5 nodes, but I want to have replicated data. So you have 1 copy, you have like, say, 3 copies of every piece of data.
Right.
Or you can shard it and say, I want a node to have 1/3 of the data, and the next node to have the second third, and the final node to have 3/3. Those are like storage options you have to come up with as you're building the system to think about how you want it to behave and how it's kind of availability. Like, can you survive with 1 node being down, that you could potentially have 1/3 of your data not available? Or if you replicate it, you can lose 1 node, your data is still in one of the other nodes.
And quorum is like what a similar option you have.
Well, the quorum is really about transaction model. So that's actually about when you have your data, which is being changed constantly, like a very high transaction rate.
Right.
When you go to query it, you want to make sure you get back the latest data. So you're telling the cluster, I want to make sure that whatever data I get back, a quorum of nodes agree that's the latest data. So that really has to do with just trying to grab data while it's changing, and you want the cluster to know, you're telling the cluster, give me the latest data that you know of.
Right, so that's all handled by Cassandra. Anyway, these kind of queries can be complex, so if you do those kind of queries, again, you pre-compute them and you have the edge directions where you want to go. Usually where you
How first was the discovery? If I give you a new problem, let's say I want to find the cheapest way to buy a song from a data or a movie. Can you extract from any portals on information about pricing, combine and create your own table of the reference, then how difficult is to explore things you didn't find?
Well, you should have to do the data in your database, right?
I'm sorry?
You have to do the data in your database somehow. So you already know how the data is stored. And then it's just how you can compute your query to find that cheapest.
Yeah, that's really like a ranking. You're talking, well, so the question was, how would you come up with, let's say, the cheapest flight? Is that what you're asking? What was the question?
My question is, how can you explore data non-specific, non-structured in other sites and prepare them for decision making and say, you want to find a place where you can buy the cheapest flight, at the cheapest price, and the day.
So there are different types of storage engines. A graph is one of them. The particular type of data query you're talking about is actually probably better done in a relational database where you have a table and you have a list of all known products and there's a price. That's a little bit easier because you're just saying, give me the list, order it by the price, and cut off the first 10, and I want the top 10. So it really comes down to the different database engines, and there's lots of debate about which one's better. And it really comes down to usage. How are you planning on using it? Your usage
The
patterns.
problem of buying a song is on so many different technology around the world that in reality you gotta go and discover ways that are more structured in the way you expect.
So that's actually the beauty of the graph databases, because what you're doing is you're taking essentially an ambiguous structure and you're applying at least a, not necessarily a structure, but a pattern. So you're saying an artist becomes a node. Now you've got all sorts of details about that artist, a name, their maybe what country they come from, what year did they start recording. You don't necessarily care about that. You might in some queries, but you don't know the subject is the artist. And then another subject is the song, and there's different details about the song. And they may not all, but maybe price, maybe not all of them has price. But they're slightly different structures. But you do know the pattern is there, and you know that an artist has recorded some songs. Just that relationship alone becomes something searchable. And you can say, give me the artist with the most songs, and you can pull that back. Or you can say, give me an artist that has recorded a song, but that song also has another artist. Maybe they did a duet. And then from those artists, give me all the recording companies, and then find all those artists from that recording company. So you can make that traversal through a graph database, even though you don't know all the structures, as long as you know the relationships, you can walk through and find it.
And that's the beauty of the graph databases, where you're really dealing with the relationship patterns, not necessarily the structure of every single node.
So let's say you have songs, and you have a bunch of nodes, and you have scores, right? You could just say, for this song, find
That's a little.
you can do it. I didn't put it here because you have to someone that you can say, this node to that node, this traverse everything, find the shortest path between them, this amount, and they can analyze it. Okay, so, okay, so let's see. So I want to know a little more complicated query. So I know that I have a ton of edges attached to the I2 that Taylor Swift has. So I want to know the distribution, how many of each type of edge I have. So again, you have Taylor Swift, you traverse to the R2, and you say, give me your incoming innings, go to the incoming, don't go to the other verses. Get the label, do a group count based on the label, and then output the result. So you see that the set of R squares have 53 edges to release groups or albums. They have 113 to actual releases for the R squares. They have to recording, they have 241, and to direct tracks, they have 1100. So I quickly analyze, okay, most of the edges are attached to the tracks, which makes sense. This is kind of a very complicated. I'm doing sort of a group count on the edge distribution that are attached to a set of vertices. Okay, so let's find the distribution of record labels that we have before the song from Taylor Swift. And let's see if she prefers one. So again, you find Taylor Swift, you go to other spreads, then you go again, traverse to all the releases that are attached to her credits. Then you go to the labels, you get the name, then you do a group count, and then you sort by the frequency of those counts, you get the first 10. So these other record labels that have corresponding, you see that 89 times by Big Machine Records, and just it doesn't have very quickly. So it happens that that's per record label. So you have most of the recordings recorded by that label. Now, you can pose a question. Does this record label records artists similar to this? Do record labels record artists that are similar? Okay, let's locate this vertex and find the distribution of the artists that they record the most. Okay, so you find that's how you put it, the place name in the Big Machine Records. Go to all the edges all the releases that you have recorded, or I don't know what is there. Go to the artist credits, then go to the actual artist, it's a few steps. Do a group count on the artist names, and then sort negative by value, get the first 10. So you can see the first one is Taylor Swift, but then you get all these ones, most of them, or all of them, are like kind of country artists. So that record label usually records people of the same genre. Okay, let's find another artist. Taylor Swift, let's say Kanye West. So I know completely similar artists, see if this happens. Let's find, that's the conclusion, so let's find Kanye West. I search for Kanye West by name, they give me one purpose. And I do the same way that I did for Taylor Swift. I go to all the credits from Kanye West, I find all the releases attached to those credits. I then go to the label, and they get the name of the label, and then I do a group count on the name of the labels, sort by the distribution and the distribution. So again, you have overwhelmingly most of the recordings by Kanye West have been recorded by Rockefeller Records. So who is this record? Let's find the distribution of the line that this record company has recorded. And if we repeat the same inquiry that I did for Adele, you will see that the distribution of artists for Rockefeller Records is JC, Kanye West, Cameron, all the other ones are hip-hop rap artists. So it's empirically, very quickly validates the claim that record labels and artists are similar. And this is some of the insight you would do in a separate, dashboard, so the right piece and the data.
But if Taylor Swift becomes a pop artist overnight, then you're kind of...
You will see the trend. So you will actually start getting the time on the credits, and then you can do the distribution by time and see when that happens.
Oh, interesting.
So the bottom line is put up that you can.
The similar artists would be for recommendation.
Right.
Like this.
Right. If you do a recommendation.
Yeah, so similarity really comes down to conditions. What do you consider similarity? Maybe do you want to put people that are over 5 feet tall? You know, or do you want people of the same style of music, or do you want people who only have Grammys? So, and that's where the personalization comes in. You can start putting in your own conditions, or it can be derived from your past listening habits. So let's say you always listen to rock music. It starts using that information to start digging through the graph, find an artist that's related with that genre, maybe in that same year or that same decade, and it starts giving you those suggestions.
Recommendation, maybe you want to recommend to Kanye West other artists you can collaborate with. For instance, you choose to try to solve. Okay, so this is one of kind of cool query. So I have these artist queries, right? This artist query cannot tell whom Taylor Swift have played song with, so who, it's sort of a collaboration link you have there, right? When she played someone featured in a song, they collaborate together. We assuming that. We're saying, okay, let's find the first tier of the direct collaborators of Taylor Swift. So I get her credits. I do a filter operation to those information and I say, okay, also I want to see the distribution with whom she has collaborated the most directly. So I need to get the artist credits and I need to sort them out, right? So I say, okay, filter them by, and then pass this function and say for each credit, get all the outgoing edges to the artist, to the other artist, find all the artist credits and count. And if that's, no, I'm sorry, so filter these edges, so you have the edges. The thing is that, let me backtrack. So in the artist credits, you have Taylor Swift featuring someone. So Taylor Swift positions here in the credit and the other number 1. So in this credits, Taylor Swift is position 1, 0 at a time. So then we find all the artists that are position 1, so the other artists that collaborate with her. And then I do a count that I have a count grade at 0, meaning that there are no positions here. And then I find all the, I found the artist that is not Taylor Swift, get the name to a group count by how many times they appear in the credit. And that's, so she has, for example, collaborated 3 times with John Mayer, 2 times with Paula Fernandez. So these are her collaborators. Now, you can pose a more interesting question. Can we recommend other people that Taylor Swift could collaborate with? So what do? We find the second tier collaborators. So what are the people that have collaborated with the people that she collaborated with? And we do distribution, and then you can fully recommend those.
Now, if you take it, I just want to throw another example. Let's say if the people who work for Taylor Swift and they want to know which other artists would actually make the most money to collaborate with. If that information was in the database, they can say, go find out all these other artists that have collaborated with other people, find out which one made the most money, and I'm going to call their agent. So they can do that.
Actually, you have the data in the music ranks. You have all the guitar players, the people composers, pretty much all that data with the final and the work. To find the second tier collaborators for new distribution, I find the direct ones, we just separated before, I put them in a set of direct. And then I do kind of the same thing, except the direct ones, so I don't repeat the artist. Do the same distribution, and then you have these ones. Now, if you look at them, there are Big Rocks, 33 times, Lil Wayne, 33, Akon, 33, so all of them are rock hip hop. So it's kind of weird that Taylor is a country artist, I would recommend all these rock artists. Now, if you
Crossover.
Sorry?
It's all about crossover.
Yeah, but if you think about it, I took all of the credits of Taylor, so she collaborated with, I don't know, one day she collaborated with one that is rock, and then you find black guy collaborators, most of them are going to be rock. And these rock hip hop artists usually, feature with a lot of artists. So when you do the whole distribution, it kind of makes sense that most of them are going to be rock people. Now, let's repeat the query, but instead of taking all the collaborators from Taylor Swift, let's take the top, the one that she has collaborated the most, the first 3. John Mayer and the other 2. So if I restrict my query to the first 3 of the direct set, and then I repeat the query, then it becomes more and more spread out. So you have some that are rap people, but all of them, some of the other ones are country artists. So that maybe the foundation makes more sense for Taylor Swift. Then you analyze the data, see how it looks, find some explanation for the driving. This is another query. Now, what are the most prolific artists that were born in Miami, according to again, you find the area of Miami. It has a lot of edges to people that were born in Miami. You transform the data because I want to bring the name on the so I do a transformation saying put in a list on artist name, and then a count of all the credit that the artist has to the recordings. You count them also, how many recordings the artist has. And then you sort by that position the credit and get the first 10. Again, you have all these 10 here. People make sense on the other solution. If I'm missing an artist, well, then we can complete the music frames that they put it there. So that's case study. If you guys have more questions, we can.
So at Senzari, and you built a recommendation engine around graphing music, right? So I know you probably can't disclose how much data you have and things like that, but can you talk about some of the types of queries that you're getting out of your database system that you're serving to your recommendation engine? Like, is it lots of traversing lots of nodes and coming back with results, and then what are your customers?
We have Cassandra, we have depends on the structure of the graph, because if I put the properties, I can put properties as nodes, right? So it depends how you count your graph. But we have, if you count the property values of all the vertices, we have 4 to 5 billion.
4 to 5 billion. Oh, you're talking about properties.
Property values.
Property values. Okay.
Depending how you structure edges. Edges we have close to 1 billion. But the last count. So, but properties mean that this is very several properties. And you could consider this a data point, because I could have a node and then some properties represent the vertices, so it's close to 4 to 5 billion.
Okay. So the types of queries that you're doing in order to serve up your recommendation engine, are you doing lots of traversals across many nodes and many paths?
We do recommendation, and then we do search API. For the search API, you do traversal. You can find the song, the albums.
So essentially it's interactive. You send in a request, it comes back with some data, and then with that data you go back and get more.
And then recommendation as well, it's an API. So you say, okay, I'm giving a recommendation for this audit, for this song, for this genre, for this decade. Now recommendation, as I said a while ago, you don't want to do a very complex operation in real time. It's going to be slow. So what do? You want to analyze all the relationships in your graph, and you derive knowledge, you derive links between people that you should recommend, and then you sort that back into the graph. And then you try to make your recommendation a simple margin of edges.
So there is a portion of it, like you said, you have to pre-compute some parts of it in order to get the speed. But that usually means that you have to have some sort of anticipation of what kind of data you're going to get. So how do you face the challenge of where somebody is looking for a specific result set, and you haven't anticipated that result set before, so you don't have it pre-created or pre-calculated? How do you, do you see that often? And then if you do, how do you face that? How do you deal with that?
So in our case, we batch process the type graph.
Okay.
You take this conclusion and then you derive knowledge. Now, you have new knowledge coming in. So for example, it's gonna be at a point that you have some part of the data that you use for the recommendation pre-computed and some part that is new. So your algorithm then becomes getting the pre-computed data, finding the data that I have not computed yet, and merging those two for the recommendation. So that's sort of the approach that you would take for data that's coming in very quickly.
Does that merger happen instantaneously?
It's code. You have to do that code in code. So you have to remember
There's a certain logic behind it. Yes, that's not going to merge irrelevant data with.
No, you guys will build this. Give me this type, give me that type, this type that I want. For example, most of the recommendations have most people don't like the same thing. So you have to start tracking what the user likes. So, okay, he likes the song, he didn't like the song, and you're tracking that through history, right? And then you have some history that you already analyze, some very recent history. Then the history say, okay, he doesn't like a short topic knowledge, but he likes this kind of tempo, he likes like that. So in your recommendation, you're kind of in real time analyze what the user likes. Maybe like, right now the user is running, right? So he wants this kind of tempo. And then you certainly you're recommended to get that information from pre-computed and real-time data, and then you need that songs to the actual user. So it's a mixture of how much you compute versus how much you get, and then you have to analyze that. And then you don't want to do it very contextualized.
Something, but there's so many layers to the graph. We have acoustic data, right? So we do deep learning on acoustic data. And that all that happens, offline, and then all that gets in. Not only do you have all the single values and time, series values of all the acoustic data in the graph, but then you have all the results about the deep learning that we've done and how the relationships of songs, how they relate to each other acoustically.
So, but that's still essentially, like you said, it's pre-computed and you know ahead of
That's
time.
right.
So based on, you know, your customers using it, you know what they're looking for. So ahead of time, you realize this is something that they could use, so I'm going to pre-compute it and put it out there, and then they can hit the API and read through it. So there's still some pre-anticipation knowing what they want.
There's no way that you could, you know, imagine we monitor, like, you know, radio station plays, and we analyze sequence, and we know that, you know, different countries sequence songs differently than in the US, right? So in Brazil, you know, a Brazilian artist might be good with Taylor Swift, where here it never happened.
Right.
So, you know, you basically have to pre-compute all this stuff, but then, you know, depending on, because, you know, we are an API, so depending on what they pass to us, when they use the API, if they pass an IP or a location, already we start creating a graph, so that's what.
So you're storing, so again, you're storing the raw data in Cassandra, and then when you're doing that pre-compute to generate the graph, that gets pulled out of Cassandra, computed by Titan, and then Titan has its own storage layer again?
Well, the recommendation is.
You store all the music information. Let's say that there are, assume that there are music data from the music. So then I can I want to derive knowledge from it. Let's say all this calculation. I dump that into a Hadoop cluster. Bash analyze the whole thing using parallel computing. I derive all the new edges. I'm going to add edges between Taylor Swift and all the people that she should collaborate on the services. So I go back to Cassandra in Titan and I say create all these edges.
Oh, okay, so you're taking the raw data, dumping it into Cassandra as a holding tank, and you pull it out into Hadoop, and then you're doing some sort of calculations.
And in Hadoop, I can do all this running work.
Right, so you're using Hadoop to analyze the data, and then you go back to Titan to put the edges in.
Yeah, the whole thing is you have to do part of it using batch analytics to derive knowledge. You have to analyze the entire graph. You do that offline to Hadoop or something else. And the whole circle is you take the data, analyze it with Hadoop or some AI tool, derive knowledge, and you have to put that knowledge back into your Cassandra store so that your software application picks it up.
Okay.
That's a whole loop. It's a loop that you run continuously.
All right, well, that's because the data coming back from music brains is not already in graph form. It's essentially just in semi-structured form.
We got concerned with the music data. That's just half of the story. You need to get your data story. So they say that we have catalog from radio playlists, we have monitor social sites. All that data we already built and put in the graph.
Yeah, so, but what I'm saying is that the music brains data that you're getting back is semi-structured, right? So you're gonna get something like XML or JSON, and you're taking that, running it through an analysis process to derive all the relationships, and then you're giving that to Titan, say, graph this.
No, Titan is not that smart. So music brains, let's say I want to do this project, right? So I take music brains, I go to the website, I add the schema, and you have to play with the data first, and then you say, okay, from Alice I want this information. I like that Alice I link to Alice Gray. So you kind of draw it in your mind, or when you do the data model. You draw. Basically, you draw this.
Right, so you derive that from the music, from what music brains is telling you.
Right, and then I write code to create in the graph to ingest.
Right.
All these very small edges and everything. And I usually do that once. The music brains, basically music brains give you a daily office, where you have to identify this office and then add new or delete artists in your graph. That's a very simple word.
Okay.
You have that data in, and you start tracking users.
So, as I said, so long before you get to the analysis part, you got a big transformation part.
Right.
Right, so you have to get that data, understand it, know what the graph is gonna look like, or at least the representation of it. And then you dump it into Hadoop to spread it out, get all the pieces you need, and then put it back into Titan to build that graph.
For example, for this size there, I don't need Hadoop. I just, simple Java program puts in Cassandra. This is not the analysis machine with Daniel and I are talking about. This is just data modeling.
Yes.
When you put it inside, once I have it in Cassandra, then I want to do centrality. I want to do the stuff. Then I do it. I download all this graph data and set the format. I use some very specific tools to drive centrality, page rank, machine learning. You do that in knowledge. Basically, you use that in knowledge, and then you put that back into a graph of probably new vertices, new edges. So I will morph this stuff with new information that I derive through machine learning. Then you have users. You want to track everything that the user does at every time and everything he's doing.
So
then you derive new knowledge.
Right. So you get your baseline data, which is the artist data, and then you have that user behavior that you're tracking, that you're just sort of collecting.
Yeah.
And then between the two of them, you say, here's your user behavior, and then you use your model of your artist history and combine the two, and gives you your recommendation.
It gets even more complicated because then we also do private graphs for our clients.
Okay.
The client might come and give us, an entire catalog that is all hand tagged.
So
So then you have to keep those graphs separated by in singles.
So when you say clients, are these like corporate clients, or you're actually building a graph for a user?
I think tomorrow, maybe I could say it, like Vivo, for example, will
Okay.
have recommendations to Vivo come to us.
Okay, so these are larger corporate clients, I mean, because that's a lot of resources to put behind saying, I'm going to build a graph for a client. You're not doing that on a
No,
per user
our
basis.
clients are record labels,
Okay.
are
It's not a per user.
streaming providers.
Yeah.
So we sort of power, I mean, today if you look at the market, we're like in the recommendation space, we're like the go-to company. Because
Okay.
before there was a company called Econes and got acquired by Spotify. So pretty much, we sort of took that load, and we're now launching a lot of, so, really our specialization is recommendations. I mean, that's really where we get, really deep and we do really unique things.
Okay,
And now we're applying it to movies, actually. We recently launched Movie Graph, which is movie recommendations, and we're basically going to continue doing that in other verticals.
okay.
So to extend the graph for movies, we didn't have to use the schema.
So your stack relies entirely on Hadoop as being a caching layer to some extent.
Hadoop is just for batch analytics. Think of it as Cassandra being a SQL database, but fully distributed, blah, blah, blah. Once you do batch analytics, which is something called Hadoop analytics, you download data into a distributed file system that is meant for batch processing. You batch processing at the same time, you do that knowledge. When you do that, you derive, this is all a process. You take everything into account. For example, you want to find global relationships there. You want to analyze your entire graph. That happens outside of your Cassandra database that is taking requests from your application. You do that knowledge, and then you take those edges and put it back into the graph. So you have one component that's for real-time processing, your software application, your website. And then you have another batch processing that you download that periodically, apply machine learning at scale, not just for one record, for all of them at the same time. You build a classifier, for example. And then you do that knowledge, you go back and put back into the graph. And then your recommendation, whatever, is much better. Then you do that, and then you have a component in the organization that uses batch process data with recent data that you have to merge with.
And all that has to be done ahead of time, prior to anybody hitting the API to get the data out.
Well, actually, we have development environments and production environments that are synced.
Okay.
They're completely different schemas, because you're getting the development graph and adding all these different things that are in production.
Right, okay.
And you need to keep them in sync because you want to put it back.
Sure.
And that's actually pretty complex.
Yeah, one problem with this NoSQL tools, yeah, they cheap, they're open source, and they dig all these tools, but they don't have the same kind of administration tool that the developer has. So you need to find people that want to really learn, that want to play with a lot of computers, that want to build systems, that want to build minor systems, and they get all that for free, but you need to have people that want to do it.
May I ask a question regarding the infrastructure itself, right? If I were to be hosting this in an AWS space or in an internal space, what size infrastructure are we kind of considering? Are we looking at first layer that handles the original core processing, core computing, and then an Hadoop stack that has X number of nodes to do all of the map producing, and then we have everything on the front end that handles that does the ETL portion of it. So in that size infrastructure, what are we really looking at? Both in an internal space or in an AWS space? And I know that this, I recognize the fact that this is not a.
So when you have to make a study, you have to first do some monitoring, you have to do some pre-analysis of how many nodes you need to get some certain performance.
Okay.
It's not that way. I mean, you can put 1 terabyte of data in a single node, it's going to fit it. If you put a 2 terabyte disk, it's just going to do its work, it's going to take a while.
But realistically, if we were to compare it to, say, I mean, you're talking about a relatively large analysis engine, is what you're talking about. So if you include all the pieces of it, so you've got the Cassandra cluster, which is running essentially your persistent store for your graph, and then you've got Titan on top of it, which is compute nodes, and then you've got the Hadoop, which is the batch processing, and I'm sure you got web servers out there that serve it. But this is not a small installation. You're talking about several dozen machines, and each one is fairly powerful with lots of compute power. Theoretically, if you just wanted to play with data just to get a feel for it, you can spin up a small server in Amazon and play with it. You know, have all the pieces on there and play with it. But if you want to do it in scale, and like run real time, you're talking about dozens of machines and probably thousands of dollars.
Yeah, the buzzword big data requires a lot of machines.
Yeah.
When we do music, machine listening, that's thousands of machines. That's really
Now,
fun.
one thing to keep in mind, Cassandra is not the fastest database to read an operation, but your performance scales with the number of boxes. They say that at 10 boxes, I read at 10 milliseconds. If I double my cluster to 20 boxes, I get 5. And you can do that real time. So that's what I mean with elastic.
To a certain point,
ability.
you get faster than 1 millisecond.
You can have one SQL database that reads in 1 millisecond. But when that database is full, then you're gonna run a lot of trouble to parallelize that and chart it on whatever. So if you think in big data, start with already planning with your NoSQL data store. It's a matter of how much you throw into, how much you can. Then you can add a caching layer, which is another layer of this.
So would you say that this between MySQL and graph database, it's the same kind of data, same relationship? It seems like graph database, which is a higher order representation of the same structure.
I could do everything I do in MySQL. It's just so much trouble. So much.
Yeah, because you have to do joins in, right?
Yeah, I have to do joins, replication. Do
Right.
replication with MySQL. It's a whole mess.
But
Yeah,
also
when you
with
try to use it.
a graph database, you have to worry about your whole infrastructure and if you have.
Yeah, but at the scale that we're doing it, you have to worry about infrastructure with MySQL as well.
Yeah, so let's say you have already a well-structured MySQL database. Is there a way, is there kind of, like an ORM layer you can use on top, where you can use these kind of graph constructs of traversing nodes?
Yeah, you can do that, but yeah, it's just that you're gonna get the benefit of operating simply.
There actually is engines, graph engines that you can put on top of relational databases. And I know MySQL is probably more common because it's open source and it's easier to integrate. There is also not so well-known storage plugins. You know, MySQL has a pluggable storage engine. So you have MySQL, InnoDB, different storage engines, and there is a graph storage engine. They don't have a whole lot of development velocity, so they're not very mature. There are, like you said, not ORMs, they're actually GRMs, which are the graph relationship model that you can put on top. Again, they're not very mature. What it really comes down to is the compute power. Get the data out and analyze it on the fly before returning it. So even if you have it stored in a relational database, let's say we're talking about standard just friends relationships like Twitter, followers. If you have a list of, a table which says follower A, user A, follower B, and then follower C and follower D, you're still going to have to go back and hit that table multiple times to find every relationship. And it doesn't matter what you stick on top of it, you still have that bottleneck. Because you're going to have to keep going back to that same table, that same spot and disk, and think about how you may have hundreds of people on the system doing the same thing, all hitting the same resource at the same
I
time.
mean, isn't that what the graph database does underneath though? Because the representation is still a
Well,
file.
the edge is the joints are half the computer, so that part is already half of the job. The other thing is that you can scale your stuff on one multiple computer, right? You get an easier way of putting these multiple edges there. You see we have. Okay, I could do this in SQL. It's just that it's gonna be a whole lot of trouble.
Well, because you have to manually shard it then.
You have to manually sort it. Performance is not gonna be the same. If one node goes down, you have a massive problem usually. You have to shard in yourself in MySQL. Not Cassandra handles that by yourself. Transparent to you.
Yeah, I mean, there are still MySQL clusters, like there's Galera and things like that.
No, I just
The
see
key-
that maybe just an easy way to kind of provide a different view into your already existing data structure.
Yes, there is, like I said, there are relationship models, like a GRM that you can put over the top of it, but there still has to be a model that you describe saying, here's the relationships and here's how to reassemble them. So it saves you a little bit on development work, because you don't, if you say, for example, if you didn't have that and you had to write queries, you have to write a recursive query that says, go find all these relationships until I run out of relationships. And then you have to analyze the results. And that is actually far less efficient with graph. See, with graph databases, they're actually designed to do that on the fly. It knows when to pull in sections of the graph, analyze it, dispose of it, move on to the next section, and you can do it in parallel.
Join and like the whole.
Yeah, so it's actually a mathematical, they're actually built specifically for that type of traversing, whereas relational databases, the actual runtime query engine is built for a different type of access pattern. And that's the key difference.
Okay, is it because of the way that Cassandra shards the graph is, it does like a closet shard?
Specifically, Cassandra handles sharding and all this stuff, specifically with the graph. That's about how time stores data in Cassandra. What kind of compression mechanism do they use? What are the sort of agents? How do they, so it's a lot of techniques for someone that they do just to make it faster. But again, if you have a traditional, if your data, you want to make another base and it's customers with employees or whatever, you don't want to do graph unless you have a lot. You want to make relationship your, your primary source of information. Do the thing you want to do. I'm not saying that the graph database is a thing for everything.
And also it's maturing quite a bit. I mean, since we started with Titan, basically Titan was an 8-person team, crazy German guy and a guy that lived in the middle of Texas, like he was from Los Alamos National Laboratory, Marco, who I brought here like a year and a half. And recently they got acquired by DataStax, right? So now they're basically going to rebuild all Titan, DataStax. So it's going to be a lot more commercially. I mean, we basically had one of the core team members of Retainer for a year and a half.
Yeah, when Marco came in, I have experience with Hadoop for several years. So I actually sit down with him, the final student that does Hadoop on time, and actually we discussed all the classes there right next to me.
But it was cool because they were committing things to the core, like right there from our office. Like as we were, fighting this stuff out. So it was, it's exciting, but it definitely took a lot of.
Yeah, it's not like you just bought the server, you have to monitor it, and you have many machines.
So it took a lot of maturity to get there.
And in comparison, how does Titan relate to Neo4j?
Yeah, the Neo4j, you have a lot more tools, more visualization stuff. It's a lot nicer to deal with. That's the purpose. But we are thinking in Senzari of a global scale. You want to track everyone, everywhere, across all sites.
Which
When you think of that scale,
Neo4j can do it. The challenge with Neo4j comes into when you get to that scale and you need to start doing lots of replication, is licensing. Because Neo4j doesn't have the same licensing model, and they will buy a jet on the pricing that you're going to pay.
Neo4j has a copy of the graph in each node.
Yeah, it is less efficient.
So if you go from a 2 terabyte node to a 10 terabyte graph, you have to change the disks.
Neo4j is really, really good for a set of known graph and a set of known relationships. Even though it's big, you can still go with a larger graph, but it's relatively known. And it's less good for more of the exploratory work. Whereas if you're going for exploratory, where that graph can be large enough, you have to traverse so much stuff, like some of the analytics that they're doing, and you have to go out to distribute it. Whereas Neo4j, it can do that, it's not quite as fast, and it's much more expensive. So that's where the tipping point is.
But we do also use Neo4j.
Okay.
So Neo4j handles certain portions of.
Oh, we use it for when we do projects and, there's, as I said, there's a lot
I
more.
want to analyze some graph. I want to put something in a graph and analyze it before I put it into production.
Yeah, so-
use Neo4j because it's always
Known set is what I'm talking about.
And it will handle, it will fit in memory easily. I don't need to worry about global scale with that one. I want to look at RMDB, that the change doesn't do to an in-memory, fully distributed database called Hazelcast. I want to do with that one.
Yeah, I've messed with OrientDB with about 40 million nodes and 400 million nodes with friends data, like friend of a friend of a friend. It's pretty good. I mean, the query language isn't quite as mature as Neo4j. I think Neo4j is a little bit more mature, but OrientDB gives you more SQL-like. You can actually write almost like SQL, whereas Neo4j has Cypher, which is almost specific for Neo4j.
That way, both support Gremlin. So
Yeah.
you can do that or
Gremlin, which is another parsing layer on top, yeah. So. Anybody have any other question? There you go.
What happened to Sparkle? I remember that was like supposed to be.
Right, actually, I think you can query using Sparkle, right?
Oh,
Yeah.
Similar one.
okay.
Yeah, you can still do it. They allow you to query that with that and it's only Gremlin.
Okay.